Hello students, I am Dr. Archana Gurjar from PharmChem Department of Principal K.M. Kundnani College of Pharmacy, Cuff Parade, Mumbai. I am going to deliver a lecture on Sigmatropic reactions. The course outcomes. The learner will be able to understand the basics of Sigmatropic reactions, the types, the schematic mechanisms, orbital mechanisms, and can identify and apply this knowledge in organic chemistry. So let's see Claisen rearrangement. 3,3 Sigmatropic rearrangement. Aryl allyl ethers, when heated without solvent, forms an orthoallyl phenol. This is the representation or the reaction. So how do you say 3,3? So for 3,3 here, the sigma bond, old sigma bond, moves to the new position and the numbering on both the sides 1, 2, 3, 1, 2, 3 gives you the new one. So this is the intermediate which is formed, and this intermediate on proton transfer gives you the final 3,3 sigmatropic product. Let's solve, or you solve this, keep on pause and try to solve it. So this is the answer for it. Now let's see aliphatic Claisen rearrangements, or also called as Claisen-Cope rearrangement. This is an aromatic moiety. So aliphatic moiety, the example, vinyl allyl ethers. The same technology. The old sigma bond transferred to the 3,3 position, that is the new sigma bond. Let's understand the mechanism. So here the old bond is broken and this is the transition state showing the new bond 3 plus 3. So 6, that is the chair shaped transition state to give you the product. Now in this, it's a substituted aryl vinyl ether. I hope you could have written the answer, the product. Now in this product, if substituent is there on the saturated carbon next to oxygen, then the double bond strongly favors trans geometry. Why so? Because if we see the mechanism, the substituent prefers an equatorial position on the chair transition state. So we can say that Claisen rearrangement is synthesis of gamma, alpha, beta, gamma, and delta unsaturated carbonyl compounds. So one such application I have given here, or the use, how this gives you the gamma delta unsaturated carbonyl compound. The orbital descriptions if we see. So in the thermal pericyclic, as per the Hoffman rule which you know, for dienes, suprafacial, and for conjugated dienes, I beg your pardon, for an alkene, suprafacial, and dienes, antrafacial components, thermal one, it should be odd. So if we see here, in this case, the alkene is giving you suprafacial 1. There is no diene, so the total sum odd. So 3,3 sigmatropic rearrangement with odd number is allowed thermally. Let's see the Cope rearrangement. It's a 3,3 sigmatropic rearrangement with only carbon atoms in the ring. So here oxygen was there, again the same thing, but only carbon atoms. So these are few examples. You can pause the video and try to give the answers, and then let's see whether you have written it right. The enol form converts to the more stable keto, and the other two answers are this. One more question I have put forth here. And this, what should be the product? Try to write it down on your own. And can this further undergo sigmatropic to give you the industrially popular citral? Can you yourself write down which one of them will be glycine, and which one of them will be cope? Let's see if you have written it correctly. So this having a heteroatom, and without heteroatom, it's a cope. One more application I want to show for 3,3 sigmatropic rearrangement. So in this, it's an enamine. So this enamine by 3,3 sigmatropic gives you adduct. We have spoken about 3,3. Now let's see about 2,3 sigmatropic rearrangements. Benzyl allyl ethers. When treated with base, the proton will be abstracted from the benzylic carbon, gives you an anion, carbon ion. The numbering as we had seen earlier in 3,3. So now the old sigma bond will be converted into a new at 2,3 position. So gives you this oxide, which can easily take up the proton to form the alcohol product. The mechanism. Now here 3 plus 2, 5. So the transition state you can see is a half chaired one and results in this product. Let's see about for the Woodward-Hoffmann rule as we had seen for the 3,3,1. We have a pi bond, a sigma bond, and a carbon ion. These already you know. So for the pi orbital, the new symbol is omega. Carbon ion has 2 negative charge, so it is gamma 2, and carbocation has no electrons, so gamma 0. If 2 new bonds are formed to the same lobe of the pi orbital of the carbon ion, then it is called as gamma omega 2 suprafacial, and different lobes gamma 2 anterofacial. So this can be described as this one, this reaction. Now here, in this case, we have only an alkene, no diene, and if you see only one component, that means odd. So this reaction is also thermally allowed. Sulfur. Sulfur is a very good at 2,3 sigmatropic rearrangement. Why? Because it can change its oxidation state by 2, so that we can start and finish an arrow on that element. It can have 2, 4, 6 oxidation states. So this is the unstable sulfinate ester which is formed, and this sulfinate ester, if you arrange it in proper way, can clearly undergo 2,3 sigmatropic rearrangement to form an allylic sulfoxide. Let's see 1,5 sigmatropic hydrogen ships. What are these? Number in the bracket 1 is old, and the new sigma bond at the 5 position again has the same 1 hydrogen. So it migrates from here to here. Now if we see the transition state, 5 plus 1, 6 membered. So this is the example, and can it have under further sigmatropic? Yes, to give you a more equilibrium flavored one. One more example I have put forth. Try to solve it and you should get the same answer. So how it happened? I have tried to show it here. The orbital picture. So as per the Woodman-Hoffmann rule, the diene component we can take HOMO or LUMO, and the CH bond as the other HOMO or LUMO. So 1,5 sigma suprafacial when the hydrogen slides across the top face, and anterofacial leaving the top face. So how to join this? Easiest way, the spherical one has only a single lobe. So wherever you draw, it will lead to retention. So link the hydrogen to top of the pi orbital, and the black sp3 orbital to the lobe of the diene, and this gives you your pi4s suprafacial component. There is only one double bond component, so again it is odd. So this 1,5 is also thermally, the reaction is allowed. So if we see the summary of the thermal sigmatropic hydrogen chips, 1,5 suprafacial easy, 1,3 anterofacial impossible, 1,7 anterofacial possible. These are the examples of 1,3 and 1,7. What happens to the photochemical one? It's just the opposite one. It follows the opposite rule. So 1,5 will have anterofacial, 1,7 suprafacial. So just let's see. So photochemical will have 1,7 suprafacial. The same funda. From the first position, wherever is that one number, it has to be shifted to the 7, and the pi, the dienes, the conjugated ones, alkenes are, pi bonds are reorganized to give you the photochemical suprafacial 1,7 shift. So thank you for the lecture.